Today, we're going to try and crack open one of the biggest mysteries in all of tech, the AI black box.
We ask these AI systems to do some pretty incredible things, right? Write our code, help diagnose diseases. But then when we ask how they came up with an answer, we usually get, well, crickets. We get the output, but the process, it's a total mystery. Which brings us to the big question for this explainer. How did these things actually think?
So this mystery actually has a name. It's called the black box problem. It's that exact moment when a super complex model like a GPT-4 just gives you an answer but doesn't show its work. The internal logic is completely opaque, making it almost impossible to figure out how it got from point A to point B. And look, this isn't some bug that can just be patched. It's a fundamental part of how today's most powerful AI systems are even built.
Okay, so let's get into it. Why can't we just, pop the hood and see what's going on in there? Well, it turns out the reasons are baked right into the very architecture of these models.
The first reason is just sheer mind-bending scale. A large language model is built on things called parameters. You can think of them like tiny adjustable knobs that get tuned over and over during training. Now, the most advanced models don't have millions or even billions of these knobs. They have trillions. So imagine trying to tune a radio, but instead of one dial, you have a trillion interconnected ones. A tiny tweak to one could change absolutely everything, making it basically impossible to trace how you ended up on a specific station, or in our case, a specific answer.
This whole opacity thing really boils down to three big technical challenges. We just talked about the insane scale, but there's also their nonlinear behavior. See, the path from your question to the AI's answer isn't a straight line. It's more like a chaotic web of firing neurons that just defies any simple kind of analysis. And finally, even the parts we can kind of see, like these attention layers that show what the model is focusing on, they don't really explain why it made a choice. They show you the what, but they totally hide the why.
And listen, this is way more than just a technical puzzle for a bunch of engineers. This lack of transparency has serious real-world consequences, especially now that we're plugging these AIs into the most critical parts of our lives.
And the stakes here are just incredibly high. I mean, think about it. If a black box AI denies you a loan, how can you be sure it wasn't because of some hidden bias? Research has actually shown AI systems penalizing job resumes with feminine-sounding words just because the training data reflected old biases. And in criminal justice, an opaque algorithm could completely undermine someone's right to a fair trial. I mean, how do you challenge a decision you can't even understand? This is how trust dies, how accountability disappears, and how really dangerous problems like bias and misinformation get spread.
So what do? We can't just throw up our hands and accept this. And this is where a really exciting field comes into play. Explainable AI, or XAI. Its entire mission is to develop the tools and techniques we need to make these black boxes a lot more transparent.
Now, within XAI, there are pretty much two main schools of thought. On one side, you've got post hoc methods. This is kind of like being a detective, trying to piece together what happened inside the black box after it's already made a decision. But on the other side, there's a more radical idea, creating inherently interpretable models. Basically, why not build AI that is transparent by design, a glass box, from the very beginning?
So let's stick with that detective analogy and look at the toolbox. Researchers are using all sorts of post hoc methods to poke and prod these models. You've got techniques like LIME and SHAP that try to figure out which words in your prompt were the most influential. You have attention visualizations that create these cool heat maps to show you what part of the text the model paid attention to. And counterfactuals are really powerful. They can show you the tiniest little change you could make to an input to get a totally different output.
And all this XAI work isn't just theory anymore. It's actually starting to have a huge impact out in the real world, turning this idea of explainability from a nice-to-have into something that really drives success.
Just take a look at the financial world. It turns out, when people are told why an AI is recommending a certain investment, they're way more likely to trust it. Bank of America found this out when they started explaining the logic behind their AI's advice. The result? Customer acceptance shot up by 41%. That's not just a small bump. That proves that transparency isn't just an ethical checkbox, it's a real business advantage.
The story gets even more powerful in healthcare, where we're talking about people's lives. When the Mayo Clinic gave its doctors a window into how their diagnostic AI was thinking, trust went through the roof. Doctors started overriding the AI suggestions way less often. But here's the really incredible part. The actual diagnostic accuracy also went up by 17%. This shows that explainability isn't just about feeling good. It leads to better teamwork between humans and AI, and ultimately, much better results.
But as promising as all this XAI stuff is, it's no silver bullet. The search for transparency is up against some really fundamental challenges that we just have to be honest about.
Yeah, right at the heart of the whole problem is what's called the accuracy explanation ability trade-off. And generally speaking, it's pretty simple. The more powerful and accurate a model is, the more complicated it has to be, and so the harder it is to explain. If you want to make a model more transparent, you often have to sacrifice some of its predictive power.
And this isn't just a hunch. People have measured it. Research from Meta actually put a number on this trade-off. Now, other labs at places like Stanford are working like crazy to close this gap, but that fundamental tension is still there. And it forces us to ask a really tough question. How much accuracy are we really willing to trade for clarity?
And that's not the only hurdle. Just generating these explanations costs a ton of computing power. And what's worse, the explanations themselves can be twisted, creating this illusion of transparency. A study out of Cornell actually showed that explanations can be deliberately engineered to hide bias, making a system look fair when it's anything but. And that's arguably even more dangerous than having no explanation at all.
So, given all these limits, how do we actually move forward? Well, maybe the most exciting new frontier isn't about trying to crack open the black boxes we already have, but about designing AI that is transparent right from the start.
The future might just lie in something called neurosymbolic AI. It's a really cool approach that aims to build glass box models by blending the pattern-matching superpowers of neural networks with the clear, structured logic of old-school symbolic reasoning. We've already seen this work in things like diabetes prediction, where a neurosymbolic model delivered really high accuracy and a completely transparent decision process. I mean, that's the dream, right? AI that's both powerful and understandable.
And that really brings us back to the final and most important question. This whole journey to open the black box, it's really a journey to build trust. It's going to be a complicated road, navigating these trade-offs between accuracy and clarity, and it's going to demand a mix of technical breakthroughs, smart regulation, and just plain old user education. Because the goal here isn't just to understand how an AI thinks, it's to build AI systems that are fair, that are accountable, and that are ultimately worthy of our confidence.